let's talk about Archimedes Principle. Then that'll lead us into how do we actually calculate the volume in this lab. So, Archimedes Principle says that for an object partially or completely submerged, so if here is my object, then this thing is buoyed. So for an object partially or fully submerged, the object is buoyed upward with a force whose magnitude is equal to the weight of the fluid being displaced. So this is Archimedes' principle. So what does this mean? So this means that if I had an object which was, say, partially submerged, so let's say it's submerged in fluid up to this point, this thing then is going to feel a force upward with a force what we call the buoyant force. Or if it's fully submerged, so let's use the yellow in this case. In this case, it still feels a force upward, which is what we call the buoyant force. Now, the reason for this is, as we'll talk about when we do fluids, what happens then is what the fluid which is above this object, so if it's the green line, you're talking about then air. If it's a yellow line, then you're talking about whatever fluid this is, so it could be oil or water or still air or anything, is applying a force downward onto this thing. This is what we call pressure. So ultimately what's happening is this thing is feeling a pressure which results itself in an overall downward force. So here we have a pressure, which that pressure then gives a force. Now down here, also what's happening is whatever fluid is below it is also pushing up onto it, i.e. from another pressure. So this is then pushing this way with another pressure, so let's call that P2, we call this one then P1, which results itself in another force F2. Now, we'll talk about this later, but basically what happens then is what you get a force down here, which is greater than the force up here, due to the fact that there is a height difference between the two. So, since there's a height difference between the two, what that means then is even though there's a force pushing downward, the overall force pushing upward is greater than that of the force downward, which means that the buoyant force then is the difference between the force pushing up and the force pushing down. So this is what we call the buoyant force. Now what this means then is, according to Archimedes' principle, that this force then, the buoyant force, is equal to the weight, which is the mass of the fluid, times the acceleration due to gravity. Now here we can then write this then as the density of the fluid times the volume of the fluid times g. So again, this is just mass, this is the density, where again, density is mass per unit volume times the volume, which is the fluid, times then g. Now, the volume of the fluid here isn't the volume of the entire fluid. So in this case, if I was talking about this entire thing had a fluid, it's not the volume of the entire fluid, but it's the volume of the fluid which is being displaced. So what that means is, for the green line here, the volume of the fluid being displaced is the amount of volume of the object which is pushing all of that fluid away. So that's this amount. If I'm talking about the yellow line, in this case, then it is simply the entire volume for the entire object. So it just depends on, so the volume of the fluid depends on how much of the object is submerged. So again, if it's partially submerged, in this case, it's only a fraction of the volume of the entire object, because that's what's actually moving the fluid. And if it's totally submerged, then it's simply equal to the volume of the object. So again, this volume here is specifically the volume of the fluid which is being displaced, not the volume of the entire fluid itself. So again, here, if it is fully submerged, so if fully submerged, then in this case, the volume of the fluid is simply equal to the volume of the object. Okay. If it's partially submerged, in this case, the volume of the fluid is not equal to the volume of the object, but it's going to be some fraction of the volume of the object. Now, why is that important? Well, that's important here because what we're doing in the lab is Mr. Pollock was fully submerging these objects in the fluid, which means that the volume of the fluid which is being displaced is exactly equal to the volume of the object. So we're going to use that when we look at our free body diagrams. So how does this pertain to our lab? So in our lab, what we're looking for then is the volume of the object, given the fact that we know the density. Right? Now, let's draw a couple quick free body diagrams. So initially what's happening is he is finding the tension out of the fluid by simply hanging the mass of the object onto here. So you have mg pulling downward. So in this case, what has to be true is what? This is a static situation. So the sum of the forces in the y direction are equal to 0. So let's simply call this the y direction. So this tells us that the tension out of the fluid minus the weight is then equal to 0. So that means the tension out is simply equal to the weight. Right? Then what he's doing is he's putting it then into the fluid. So what's happening here is here's now our fluid. Here is now the object fully submerged. So you still have mg down. But what happens is he's actually registering a new tension, which is what we call the apparent weight. So basically what's happening is when he puts it in here, he's now measuring a new tension, which is less than the tension out of the fluid, even though the mass of this object hasn't changed, which means that the gravitational force hasn't changed. Now, what's different is, as he said in the video, there's now a buoyant force acting on. So if I look at the free body diagram in this case, I would still have this TO this way, but then I also have a buoyant force acting on it this way. So here's my buoyant force, which basically means that what? If I want to know what is the buoyant force, I'm simply going to take the tension out of the fluid minus then the tension in the fluid, and that is going to give me simply my buoyant force. So let's write that down. So what we now know is that the tension out of the fluid minus then the tension in the fluid must then be equal to the buoyant force. Well, now we know the buoyant force is simply equal to the density of the fluid times the volume of the fluid times the acceleration due to gravity. But since this object is fully submerged, we know in this case then is that the volume of the fluid displaced is the same thing as the volume of the object. So this is the same thing as the density of the fluid times the volume of the object times the acceleration then due to gravity. So here, what we're looking for then is the volume of the object. Well, all we have to do now is solve this expression for the volume of the object. So from here, this tells me that the volume of the object then is equal to the tension out of the fluid, which is simply equal to the weight of the object, minus then the tension in the fluid, all divided by the density of the fluid, times the acceleration due to gravity. So, when you're looking at then, when the object is fully submerged in the fluid, i.e. for the water, for the vegetable oil, and for the isopropyl alcohol, in this case, you simply want to take the weight of the object, which is the mass of the object times the acceleration due to gravity, minus that of the tension that he reports, which is going to be the mean tension, inside of the fluid, divided then by the density of the alcohol, or the vegetable oil or water, which he also says in the video, and divide also by the acceleration due to gravity, and then that's going to give us the volume of the fluid, which is also equal to the volume of the object, in units of meters cubed. So in this case, if you want to report it in centimeters cubed, it doesn't really matter. We just have to do a conversion from there. So again, the way you're going to calculate it is through the direct mass of the object. So in that case, as long as you know the mass and you know the density, then you can find the volume. Again, by simply saying that what? The density is equal to the mass divided by the volume, which means the volume then is equal to the mass divided by the density. And then the indirect measurements of it are then going to be through the 3 different fluids that you're measuring each one in. This is going to happen for both of the 2 objects. From here, you can then find discrepancies and basically find the average volume of each one of these objects. Right? So again, all this has to do with, again, Archimedes Principle, which says that any object which is partially or fully submerged in a fluid feels an upward buoyant force due to the fact that the pressure at the top is less than the pressure at the bottom, which results itself in a total upward force. Here, I'm standing in air. Since I'm standing in air, that's what we call a fluid. We'll talk about this more when we talk about fluids. What that means is that ultimately I'm being buoyed upward due to the fact that I'm in air because the pressure above me is less than the pressure below me. This is true for any type of fluid that we put an object into.